This is part 2, a direct follow-up to my last video, why solar panels are tilted at this exact angle. If you haven't seen that one, watch it first, the link is in the description, because here we pick up exactly where it left off. We ended on a simple rule of thumb: set your panels tilt roughly equal to your latitude. For Kathmandu, at 27.7 degrees north, that gave a tilt of about 28 degrees. But a rule of thumb is just that, a shortcut. So the obvious question is it actually right? And if we wanted the truly optimal angle, how would we compute it? In this video, we'll answer both with Python, building up the real solar geometry step by step, the sun's declination, the hour angle, the angle of light on a tilted panel, and finally sweeping every tilt to find the one that captures the most energy over a whole year. First, the sun doesn't sit at the same height all year. Because Earth's axis is tilted by about 23.5 degrees, the sun appears to drift north and south through the seasons. We call that angle the declination. There's a classic formula for it, Cooper's equation. In Python it's just one line: feed it the day of the year, and it returns the declination in degrees. Check it against the calendar and it lines up exactly, near zero at the equinoxes, plus 23.45 at the summer solstice, and minus 23.45 at the winter solstice. Next, the sun moves across the sky every day, from sunrise in the east to sunset in the west. The hour angle measures how far the sun is from its highest point, solar noon. At noon the hour angle is 0. It's negative in the morning, positive in the afternoon, and the value at sunset tells us how long the sun is above the horizon that day. The sunset hour angle comes straight from the latitude and the declination we just computed. A few lines of Python, and we know the day length for any date. Now the key quantity. What actually matters is the angle between the incoming sunlight and the direction the panel faces, its normal. Call that angle theta. The smaller theta is, the more directly the light hits, and the more energy the panel collects. The whole game is keeping theta small. And here's the payoff, that cosine of theta is one clean line of Python, built entirely from latitude, declination, the hour angle, and the panel's tilt. Everything we've assembled, in one function. Now we put it all together. For every possible tilt, from flat to steep, we add up the energy collected across an entire year. Then we just ask Python which tilt wins. Plot the result, and a clear shape appears, a gentle dome. Energy climbs as you tilt up off flat, peaks, then falls away as the panel gets too steep. And the winner? 26 degrees. That's the tilt that captures the most energy over the whole year, for Kathmandu's latitude. But here's the beautiful part. The rule of thumb said 28 degrees. The true optimum is 26. Just 2 degrees apart, and because the dome is so flat near the top, the energy you'd lose by using the simple rule is essentially 0. The shortcut was right all along. So there it is. We started from the geometry of Earth's orbit, built it up in Python step by step, and proved that the simple latitude rule really does get you essentially the perfect tilt. And the best part, change one number, your latitude, and this same code gives the optimal tilt anywhere on Earth. The full script is linked in the description, so you can run it for your own location. Next, we leave solar behind and head into the wind. We'll start tearing into how wind turbine blades are actually designed, blade element momentum theory, from the ground up. Subscribe to Python for Engineers, so you don't miss it.